Good day. This is Jackie Lucy Lagos and welcome back again for another episode of BSED Math or Linear Algebra. So for today's topic, we will be focusing on matrices and matrix operations. Our target learning outcomes are the following. At the end of the session or sessions, the pre-service teacher should be able to define matrices and the dimensions of a matrix, solve operations of addition, subtraction, and multiplication involving matrices, and determine whether the product of two matrices are defined. So let's begin with some matrix notation and terminology. First, we have definition 1. A matrix is a rectangular array of numbers. The numbers in the array are called the entries in the matrix. So we have here examples of matrices. We have a 3 rows and 2 column matrix. So these are 3 rows and column matrix. We have a 1 row and 4 columns matrix. We also have a 3 rows and a 3 column matrix. We also have a 1 column or 2 rows, 1 column matrix. And we have a 1 row and 1 column matrix. Now the size of a matrix is described in terms of the number of rows or the horizontal lines and columns or the vertical lines it contains. So from our examples, we have here 3 rows and 2 columns. So it is a 3 rows and 2 columns matrix. It is denoted by 3 by 2. It is called a 3 by 2 matrix since 3 here is our number of rows and 2 is the number of columns. We also have a 1 by 4 since there is only 1 row and 4 columns. We also have a 3 by 3 matrix. There are 3 rows at the same time there are 3 columns. So this type of matrices are those that are called square matrix since they have the same number of rows and they have the same number of columns. We will explain it further later. Then we also have a 2 by 1 matrix. There are 2 rows and 1 column. Then we have a 1 by 1 matrix since there is only 1 row at the same time 1 column. Now let's proceed with a matrix with only 1 row is called a row vector or a row matrix. So it is in the form 1 by n. Since 1 here represents the number of rows and it is only 1 for a row vector. And n here can be any number and it represents the number of columns on that matrix. Then we have here an example. It is a 1 by 4 matrix. There is only 1 row and 4 columns. Now, a matrix with only 1 column is a column vector or a column matrix. So it is in the form n by 1. So n here is the number of rows and we have 1 which is constant, the number of columns. The example, we have a 2 by 1 matrix. There are 2 rows and only 1 column. Then we have A sub ig. So it denotes the entry that occurs in row I and column j of a matrix A. So I here represents or denotes the row and j denotes the column. So a general M by n matrix is written as follow. So we have a matrix A, then its entries are the following. A sub 1 1 wherein 1 represents the place wherein it is on the first row and another one represents the column. So this A sub 1 1 means an entry in row 1 and at the same time column 1. So if we say A 2 2, so it is on row 2 and at the same time column 2. So if we say A sub 1 2, so it is on row 1 and column 2 up until A sub 1n, wherein n here represents the number of column. And at the bottom part, we have A sub m1, wherein m here represents the number of row until it goes to A sub m sub n, wherein m is the number of rows and n is the number of columns. Hence, it is called an m by n matrix. And then we will have when a compact notation is desired, the preceding matrix, so this matrix A here, can be written as A sub ig sub m by n, or just simply A sub ig. So again, I here represents the row, and j represents the column. So another one, a matrix A with n rows and n columns is called a square matrix of order n. And the shaded entries A sub 11, A sub 22, up to A sub nn in the matrix below are said to be on the main diagonal of A. So, as what I have mentioned a while ago, n by n columns or matrix means that we have the same number of rows and we have the same number of columns. And it is called a square matrix of order n. And A sub 1, 1, A sub 2, 2, up to A sub nn here is our main diagonal or the main diagonal of the square matrix A. Now we have operations of matrices. So under this topic, we have definition 2. Two matrices are defined to be equal if they have the same size and their corresponding entries are equal. So we can say that the matrix or two matrices are equal if and only if they have the same size, meaning they have the same row and they have the same column, and at the same time the entries and the corresponding locations of the two matrices are the same. So we have here, it means that if A is equal to A sub ig and B is equal to B sub ig, and they have the same size, then A is equal to B if and only if A sub ig is equal to B sub ig for all I and j. So, for all entries in the ith row and jth column are the same, then these two matrices are said to be equal. We have here an example. We have a matrix A, 2, 1, 3x. We have matrix B, 2, 1, 3, 5. Then we have matrix C with entries 2, 1, 0 and 3, 4, 0. So if we will notice, A matrix A and matrix B have both 2 by 2 or both 2 by 2 matrices. So it has 2 rows and 2 columns. Same goes with B. While in C, it has 2 rows and 3 columns. So it is different from A and B, matrix A and B. Then if x is equal to 5, then A is equal to B. So here, if x here is equal to 5, then it will have the same entries on matrix B. Hence, these two entries, these two matrices will now be equal. Thus, for all other values of x, the matrices A and B are not equal. So if the values substituted to x other than 5, it won't make the two matrices equal anymore. So only 5 can satisfy the conditions that it must have the same size and must have corresponding entries that are equal for us to say that matrix A and matrix B are equal. Then there is no value of x for which matrix A will be equal to matrix C, since matrices A and C are of different sizes or have different sizes. So from our condition, it must have the same size. The two matrices must have the same size for it to be said equal. So here, matrix A and B are 2 by 2 matrices, while C is a 2 by 3 matrix. So it can't be the same to either matrix A or matrix B. While matrix A and B can be the same only if and only if the value of x is equal to 5. So moving further, we'll proceed to definition 3. If A and B are matrices of the same size, then the sum A plus B is the matrix obtained by adding the entries of B to the corresponding entries of A. And the difference A minus B is the matrix obtained by subtracting the entries of B from the corresponding entries of A. And in this definition, it is important to note that matrices of different sizes cannot be added or subtracted. So in matrix notation, we have if A is equal to A sub ig, so this means that ith row and jth column. Same with B sub ig, or and it have the same size, meaning the rows of matrix A is the same with the number of rows of matrix B. And also with the column, they have the same column, hence they have the same size. Then the sum of the two matrices can be obtained by adding each entry of matrix A to the corresponding entry of matrix B. So, adding entries of the same row and the same column. Same goes with the difference. So, we'll just subtract the entry of matrix A with the corresponding entry in matrix B. So we have here an example. We were given three matrices with matrix A, a 3 by 4 matrix, matrix B, a 3 by 4 matrix, and matrix C, a 2 by 2 matrix. So from here, we can infer that only A and B can be added or subtracted, while C cannot be added nor subtracted to either matrices A and B. So here we have a sum. We have here the sum of matrix A and B. So we'll just add corresponding entries. So 2 plus negative 4, that's negative 2. 1 plus 3, that's 4. 0 plus 5, it's 5. 3 plus 1, that's 4. So negative 1 plus 2, that's 1. 0 plus 2, it's 2. 2 plus 0, that's 2. Then we have 4 plus negative 1, that is 3. 4 plus 3, that's 7. Negative 2 plus 2 is of course 0. 7 plus negative 4, that's 3. Then we have 0 plus 5, which is equal to 5. So this matrix here is the sum of matrix A plus B. And we obtained this the entries of this matrix by adding the corresponding entries of matrix A and matrix B. Now their difference, same procedure, but this time we will subtract the corresponding entries. So we have 2 minus negative 4, that's 6. Since the sign of the subtrahend is negative, so we'll change it to positive and proceed to addition. So 2 minus negative 4, that is positive 6. Then we have 1 minus 3, that's negative 2. 0 minus 5, that is negative 5. Then 3 minus 1, that is 2. Negative 1 minus 2, that is negative 3. 0 minus 2, that's negative 2. 2 minus 0, that's positive 2. 4 minus negative 1, that is 5. 4 minus 3, that's 1. Negative 2 minus 2, that is negative 4. 7 minus negative 4, that is 11. Then 0 minus 5 is equal to negative 5. So this is the difference of the two matrices. The matrix here is the difference of the two matrices A and B, and we obtain the entries of this matrix by subtracting corresponding entries of A and B. Then the expressions A plus C, B plus C, A minus C, and B minus C are undefined. Why? Because they have different sizes. So the size of matrix A is 3 by 4, while matrix C is 2 by 2. Same goes with matrix B and C. So we cannot add nor subtract them, so these expressions are undefined. Then we'll proceed to definition 4. If A is any matrix and C is any scalar, then the product CA is the matrix obtained by multiplying each entry of matrix A by the scalar C. Then the matrix CA is said to be a scalar multiple of A. In a matrix notation, so if A is equal to A sub ij, wherein I is represents the row and j represents the number of columns, then CA sub ij is equal to CAIG CAIG. So this means that each entry of matrix A will be multiplied by the given scalar, and we will come up with a scalar multiple of that matrix. Example, we have matrix A with entries 2, 3, 4, 1, 3, 1. With a scalar of 2, this will be multiplied, or all entries of matrix A will be multiplied by 2. Then we have 2 times 2, that's 4. 2 times 3, it's 6. 2 times 4, that's 8. 2 times 1, 2. 2 times 3, that's 6. Then we have 2 times 1, which is 2. So this matrix here is a scalar multiple of matrix A by 2, since we multiplied all entries by 2. So it is a scalar multiple of matrix A by 2. Another example, we have matrix B with entries 0, 2, 7, negative 1, 3, and negative 5. Now, our scalar here is negative 1. So, same procedure, we will multiply each entry of matrix B by negative 1. So, negative 1 times 0, that's 0. Negative 1 times 2, that's negative 2. Negative 1 times 7, that's negative 7. Negative 1 times negative 1, of course, it's positive 1. Negative 1 times 3, that's negative 3. The negative 1 times negative 5, it's positive 5. So this time, we have a scalar multiple of b by 1, by negative 1, since we multiplied all entries by negative 1. Then we have another example, matrix C with entries 6, 9, negative 6, 3, 3, 0, and 12. So we have a scalar multiple of matrix C here by 1/3, since we will multiply all entries of C by 1/3. So 1/3 of 9, that's 3, 1/3 of negative 6, it's negative 2, 1/3 of 3, that's 1, 1/3 of 3 again, that's 1, 1/3 of 0 is 0, and 1/3 of 12, it's 4. So here we have a scalar multiple of matrix C by 1/3, since we multiplied all entries by 1/3. Then it is a common practice to denote negative 1b by negative b. So we can write, instead of writing negative 1 times matrix b, so we will just write negative b, and it is understood already that our scalar is negative 1. And therefore, we will multiply all entries of matrix b by negative 1. Now, we will proceed with matrix multiplication. So we have here definition 5. If A is an M by R matrix and B is an R by N matrix, then the product AB is the M by N matrix whose entries are determined as follows. To find the entry in row I and column J of AB, single out row I from the matrix A and column J from the matrix B. Multiply the corresponding entries from the row and column together, then add up the resulting products. So we have here the definition of this matrix multiplication requires that the number of columns, so that is M by R here, R, of the first factor or the first matrix must be the same as the number of rows of the second factor. So here, R by N, that is R, it must be the same to the number of columns on the first matrix in order to form the product AB. So in order for us to multiply the two matrices. Otherwise, if this condition is not satisfied, then the product is undefined. So if here, writing side by side the sizes of the two matrix, the inside number must be the same or equal before we can proceed with matrix multiplication. And we can determine the size of our matrix by combining the outside numbers. That is the size of our product matrix. Otherwise, if these two number here, the inside numbers are different, then the product is undefined. So we have here an example. We are given a matrix A 2 by 3 matrix with entries 1, 2, 4, 2, 6, 0, with matrix B, a 3 by 4 matrix with entries 4, 1, 4, 3, 0, negative 1, 3, 1, 2, 7, 5, 2. So since A is a 2 by 3 matrix and B is a 3 by 4 matrix, the product AB is a 2 by 4 matrix. So if we write this side by side, we can see that the number of columns of matrix A is the same as the number of rows of matrix B. Hence, we can proceed with matrix multiplication. And our size, or the size of the resulting matrix or the product matrix AB, will be 2 and 4, since the number of row here is 2 and the number of columns of the second matrix is 4. So it is a 2 by 4 matrix. Now let's proceed to the computation. To determine, for example, the entry in row 2 and column 3 of AB, we single out row 2 from A and column 3 from B. Then as illustrated below, we multiply corresponding entries together and add up this product. So our second row entries are 2, 6, 0, and our third row column entry for matrix B is 4, 3, 5. So we'll multiply 2 times 4 plus 6 times 3 plus 0 times 5. That will give us 26. And that will now be the entry for row 2, column 3 of our product matrix. Then the entry in row 1 and column 4 of AB is computed as follows. So this time, we have row 1, that's 1, 2, 4. Then we have column 4, that's 3, 1, 2. Then we will multiply corresponding entry. So 1 times 3 plus 2 times 1 plus 4 times 2, then we will come up with 13. Since 1 times 3, it's 3, plus 2 times 1, that's 2. So 3 plus 2, it's 5, plus 4 times 2, which is 8. So 8 plus 5, it's 13. So this will now be the entry for row 1, column 4 of matrix AB. And then the computations for the remaining entries are, this is for row 1, 1, 4, 2, 0. Row 1, column 1, this one, 12 here, 1, 4, that's 4, 2 times 0, that's 0, 4 times 2, that's 8, so 8 plus 4 is 12. Then we have 1 times 1, this is first row, second column. 1 times 1, that's negative, that's positive 1, minus, since we have 2 times negative 1, so minus 2 times 1, that's negative 2. So do we have 1 minus negative 2, that's negative 1, plus 4 times 7, that's 28. So plus 27, plus 28 is equal to 27. So that is row 1, column 2. Then we have row 1, column 3. So this one and this one. 1 times 4, that's 4, plus 2 times 3, that's 6, that's 10, 4, plus 4 times 5, that's 20, so 10 plus 20, it's equal to 30. Then we have 2, row 2, and first column, so 2 times 4, 8, plus 0, that's 8. 2 times 1, that's 2, minus 6 times negative, so plus 6 times negative 1, or minus 6 times 1, so that's 6. 2 plus 6, that's 8, plus 0 times 7, 0. 2 minus 6, that's negative 4. And we have 2 times 3, 6, plus 6 times 1, that's 6, 12, plus 0, that's 12. So we have here row 2, column 4. So these are now, or this is now the matrix, the resulting matrix, the product matrix of matrices A and B. So it is a 2 by 4 matrix. Now let's give another example. So if we have here matrix, we have 2, if we have a 2 by 3 matrix, we just input the entries of our matrix here. We have we have 1, 2, 3. Then below we have 4, 5, 6. So that is our first matrix. Then we'll add another 1, we have here 1, 2. We have 3, 4, 5, 6. So these are the entries of our matrices. Now we will, of course, first we need to check if our product is defined. So how? So let's use the way on how to check if we have a defined product. So we will write the size of our first matrix, which is 2 by 3. 2 by 3. Then the other one, that is 3 by 2. So from here, we can say that our product is defined since the inside number is equal, that is 3 is equal to 3. Then our resulting matrix is 2 by 2. So this is equal. Then we have this 2 by 2 matrix as our product matrix. So that is a 2 by 2 matrix. Now let's proceed to the computation. So in order to have a in order to have, change the color. Okay, vertex 2. So in order for us to get the entry for our 2 by 2 matrix, so we need to take or single out, of course, that's row 1 and column 1. So that is our first, that the product of this would be the entry to our first or to our product matrix. So that would be 1 times 1, 1 times 1 plus we have 2 times 3, 2 times 3 plus 3 times 5. We have 3 times 5. So this is the first entry of our product matrix. Now we'll proceed with the second row, first column. So that would be second row, first column. So this one here. Okay, that would be 4 times 1. Then plus 5 times 3. We have 5 times 3 plus 6 times 5. 6 times 5. So that would be our second row, first column mat entry of our product matrix. Now let me just erase this first because I might like lock a space. Then we will proceed with the second row, second column entry. Second or first row, second column entry. So that would be first row, then we have second column. So that would result or give us first row, that's 1 times 2 plus we have 2 times 4. 2 times 4 plus 3 times 6. That is 3 times 6. Then we will proceed with the second row, second column. So that would be from second row, second column also. Okay. Then that will give us 4 times 2. 4 times 2 plus 5 times 4. That's 5 times 4 plus 6 times 6. So that would close our product matrix. Now return back to red. Okay. Now, then we will have, what do we have here now? So let's solve each entry. So we have 1 times 1, that would be 1, plus 2 times 3, that would be 6. So that is 6. Let me use the text button so that it won't be easier. So we have 1 times 1, of course 1, plus 2 times 3, that's 6, plus 3 times 5, that's 15. Then we have our second row, first column entry, 4 times 1, that's 4, plus 5 times 3, that's 15, plus 6 times 5, that's 30. Then we will proceed with the second column or the first row, second column. So that would be 1 times 2, that's 2, plus 2 times 4, that's 8, plus 3 times 6, that's 18. Then below, that is 4 times 2, that's 8, plus 5 times 4, that's 20, plus 6 times 6, that's 36. So that will close our matrix. Okay, now let's simplify further. That would be Let's proceed to addition. So our matrix now will be 1 plus 6 plus 5 plus 15. 1 plus 6 plus 15, that is 22. So we have 22. Then 7 plus 15, that's 22. Then we have 4 plus 15, that's 19 plus 30, that's 49. Okay, that's 49. Then we have 2 plus 8, that's 10 plus 18, that's 28. Then we have uh, 8 plus 20, that's 28 plus 36, that's 56, 64. 64. So that is our answer for these two matrices here. Multiplication of matrices of two matrices. So this is our answer. 22, 28, 49, 64. Now we will proceed to determining whether the products of our matrices are defined. So this is our convenient way of identifying these matrices if they are defined. So here, suppose that A, B, and C are matrices with the following sizes. We have matrix A 3 by 4 matrix, matrix B, a 4 by 7 matrix, and matrix C, a 7 by 3 matrix. Then by using the convenient way, this we here that was discussed previously, AB is defined and is a 3 by 7 matrix. So AB, that is AB, 3 by 4, 4 by 7. So 4 is equal to 4. So 3 and 7 will be the size of our matrix, AB. Then we have BC is defined. So BC, we have 4 by 7, 7 by 3. 7 is equal to 7, so it is defined. Then 4 by 3 is the size of matrix BC. Then we have CA. CA is defined, so it will transfer A here. So that would be 7 by 3. Then we have 3 by 4. So 3 and 3 are equal. Then we have 7 by 4 as our matrix, or the size of matrix CA. On the other hand, the products AC, CB, and BE are all undefined. Why? So here we have AC, 3 by 4 and 7 by 3. Of course, 4 is not equal to 7, so it is undefined. We have CB, 7 by 3 and 4 by 7, so it is not also defined since 3 is not equal to 4. Then we have BA, wherein B is 4 by 7 and A is 3 by 4. So still 7 and 3 is not equal. Therefore, the product BA is also undefined. In general, if A, matrix A, is equal to AIG is an M by R matrix, and B is equal to BIG is an R by N matrix, then as is illustrated by the shading of the following display, AB, we have the matrix AMR matrix, and we have a BRN matrix. Then the entry ABIG in row I and column J of AB is given by ABIG is equal to AI1 BI1 J B1J. So this one. Then add AI2 B2J AIR BRG. Then this formula is called the row column rule for matrix multiplication. So row and a column rule. So that is how we are going to get the entry of our product matrix. Then add all of the products, then we will have the entry of our matrix. So that is our topic on operation of matrices. So that would be all. I hope you have learned something from our discussion today, and see you again on our next episode for BS Ed Maten or linear algebra. Again, this is Jackie Lucy Lagos, and have a good day, everyone. Thank you.